In this video, we want to discuss some examples on the use of the Fourier transform and the power spectrum, as well as some other things. So just some wrap up of materials in Chapter 3. First, I want to look at an example where we're just going to generate a waveform. This is a filtered waveform that consisted, I believe, of two sinusoids that were filtered along with some noise. So we construct actually it's just filtered noise looks like. So we construct a 512 point Gaussian noise array. And then we're going to filter it by averaging segments of 3 consecutive samples to produce a new signal. And what we would expect is that this would basically have a filtering effect. So what we're going to do is actually the convolution between the signal and a 3-point array having elements 1/3, 1/3, 1/3. So just notice in the interpretation, this is not one vertical bar 3, this is 1/3, 1/3, 1/3. And then we want to find the power spectrum of the filtered noise using the direct method. So before showing the example, I want to discuss a little bit about convolution and what is convolution. So the easiest way to think about convolution is to think about it graphically. In this case, we have two signals, F and G. What we do when we do F convolved with G, is we basically take G and F and we flip G. And the reason that you do this is that you want the times to correspond. So in convolution, we're usually concerned about a time domain effect. And remember, the values of G on the left-hand side are for the lower values of time. And as you move to the right, you're increasing the value of time. So if you want to take the initial value of G and look at it with the initial value of F, you have to flip G. So unlike cross or autocorrelation, where we take or cross correlation, where we take one signal, we move it back and we slide it across. In convolution, we flip it, and that's because of the time domain effects that are present with convolution. Cross correlation we're often using just to, for example, determine the relationship between two data sets. Convolution, we're often looking at the relationship between two temporal signals. Now, MATLAB in convolution basically will do this flip and slide thing. So here is the creation of this data set with sampling frequency. And then here's our 0.3, 0.3, 0.3 filter. The waveform is constructed here with X, just basically a random number, and then Y is a convolution of X comma B. So basically MATLAB is going to take B and flip it, which in this case doesn't matter since it's a square array. It's going to slide it across, doing the slide and multiply, slide and multiply, slide and multiply. So this is the output and what the frequency spectrum looks like. You can look back in Chapter 2 to see the original frequency spectrum of this, and you'll find that it basically just is not as smooth. So this 0.3, 0.3, 0.3 convolution has the effect of smoothing the waveform because it's taking a moving average, a 3-point average at one time. So now we're going to repeat that example, same signal. The difference here is we're going to use a Welsh averaging method. Two different segment lengths, a 256 segment length and a 32 segment length. We'll use the default window, which I believe is the Hanning window, and a maximum overlap. And then we'll use a subplot to show two different power spectra on the same graph for comparison. So this is an important algorithm because I'm going to want you to basically do the Welsh method with the data set we have been given in class. So here's our original spectrum of that signal. And then here's what happens when we use the Welsh method with a window size of 256 and the Welsh method with a window size of 32. So you can see that you'd certainly lose a great deal of structure as the window size becomes smaller. A lot of the finer points here are going away, and you're getting more of just a smooth looking spectrum. In fact, the spectrum looks quite different because you see sort of this energy concentration that looks more just sort of overall functional instead of peaky. Now, this is just a quick illustration on the effects of a window choice. If you don't window, either MATLAB will default or you will effectively be using a rectangular window. And this is the frequency spectrum of different windows. So you can see, and of course, obviously, these are sort of normalized to be the same sampling rate and the same length in time, so that we're comparing apples and apples. So for example, on a rectangular window, we have this zero gain, and then suddenly we see that we go into 30 dB down at about 20 hertz. And then beyond that, the rectangular window is fairly significantly reduced. So by the time you're out to 100 hertz here, you're 20 dB down, which is, pretty significant amount of decay. That's an order of magnitude. So any effects of the rectangular window are going to be pretty much minimized in this example by the time you get to 100 hertz. The Hamming, on the other hand, has a kind of a flatter region. It does a little reduction even at DC levels, so you're getting some reduction even before you increase in frequency. You can see this is a little bit broader. So what you would expect from the Hamming window is you would expect the magnitude of your signal to be somewhat reduced. But since it's kind of broader and flatter, you would expect out to probably 50 hertz. That the Hamming window would not have a huge impact on your signal. The Blackman-Harris is similar. It's a little broader in band. You do get a little more amplitude reduction of the signal. The side lobes are significantly reduced, not so much so in the Hamming window. So remember, in the frequency domain, these signals would be convolved in frequency. So your Hamming window, your Blackman-Harris window, and your rectangular window are all going to provide some filtering effect themselves. So here's an example in the time domain of a signal, and we have applied a Blackman-Harris window here. So here's your window, and here's what the signal looks like after the application of that window. This is a little bit exaggerated. Normally, you would want your window length to run pretty much the signal length. So in this example, there's just a little bit of exaggeration, just so that you can see sort of what it looks like. But you can see these peaks on the end are getting attenuated. So here's an example then of what the frequency spectrum of that signal or a similar signal would look like. So in this signal, we clearly had a couple of sinusoids, and then we had what was most likely some noise. So what you find is that with the rectangular window, the peaks are very well reproduced. When the Hamming window is applied, you can still sort of distinguish the peaks. But notice there's a little bit of amplification showing up in the side lobes. And then notice on the Blackman-Harris, there's even more amplification and broadening of these side lobes in the frequency plot. And these two peaks are no longer distinguishable. So we've certainly lost some resolution as we've gone from a rectangular to a Blackman-Harris. We've also introduced what are probably some spurious structure into the frequency plot. because of the effect of the window. But what we've gained is we've gained a smoother looking spectrum. That's because we're less likely to have those edge effects that would show up in a rectangular